Hi, today we'll be talking about our time series assignment. I'll briefly explain the assignment problem statement and my solution. So, Global Mart is an online store supergiant having worldwide operations. It takes orders and delivers across the globe and deals with three major product categories: consumer, corporate, and home office. The store caters to seven different market segments and in three major categories. The intention of this case study is to forecast the sales and demand of Global Mart for the next 6 months that would help manage the revenue and inventory accordingly. We find that the two most consistently profitable segments and use classical decomposition and auto-ARIMA models for forecasting. We then forecast the sales and demand for the next 6 months using the most suitable model. The model indicates that sales are expected to grow for the EU region but will follow the expected seasonal trend. An average demand is expected to be 756 units for EU and 804 for APAC, so adequate inventory needs to be planned for. Now, classical decomposition is used to isolate the trend, seasonal, and other variable components from a time series model. We attempt to explicitly detrend and deseasonalize the time series using curve fitting. Good choice of trend and seasonal patterns will essentially imply that the residue after stripping the time series of the trend and seasonality that we have identified will be stationary. ARIMA stands for Autoregressive Integrated Moving Average Model. ARIMA is a forecasting technique that projects the future values of a series based entirely on its own inertia. Its main application is in the area of short-term forecasting. So, three broad classes of practical importance are the autoregressive models, the integrated models, and the moving average models. So these three classes depend linearly on previous data points. A combination of these ideas produce the auto-regressive moving average, which is the ARMA, and the auto-regressive integrated moving average, which is the ARIMA models. Now, smoothing is the process of making the curve smoother by averaging out the noise to make the trend and seasonality more apparent. Time series data is important when we are predicting something which is changing over time using past data. In time series smoothing, the goal is to estimate the future value using the behaviors in the past data. There are many statistical techniques available for time series forecasting. One is the simple moving average, one is the exponential smoothing, and then you have the autoregressive integration moving average. Now, white noise is a time series that is pure noise, which means it does not have structured behavior that can be modeled. A time series consisting of uncorrelated values, each with zero mean and the same variance, is also called white noise. Now, a crucial test for any time series analysis is that after modeling is done, we need to finally check if the residues after removing the predicted values out of the original series has the characteristics of white noise to confirm if our modeling exercise is successful. So some commonly used tests for this are the sample autocorrelations, using Yule-Walker algorithm, turning point test, difference sign test, runs test, rank test, explicit tests for normality, etc. Now, we pose this as a hypothesis test, with null hypothesis being the residual time series consists of uncorrelated samples from a Gaussian series, and the alternate hypothesis being the time series has correlation between values observed at different times that cannot be ignored. We use a predefined significance level, alpha, and alpha represents the threshold for the probability that we'll make an error if we reject the null hypothesis. So the null hypothesis is rejected, that is, we decide that the residual series is not white noise if and only if P is less than or equal to alpha. Now around stationarity. Now, stationarity of a time series refers to the time invariant relationship it exhibits between values seen at different timestamps. In other words, any given sequence of values is equally likely to appear starting at any time in the overall time series. Stationarity is one way of modeling the dependent structure. It turns out that a lot of nice results which hold for independent random variables hold for stationary random variables. And of course, it turns out that a lot of data can be considered stationary. So the concept of stationarity is very important in modeling non-independent data. Example, if we consider the forecasting problem, how do we forecast? If everything's different tomorrow, then it's impossible to forecast because everything's going to be different. So the key to forecasting is to find something that will be the same tomorrow and extend that to tomorrow. Now in time series analysis, the partial autocorrelation function, which is the PACF, gives the partial correlation of a time series with its own lagged values, controlling for the values of the time series at all shorter lags. Whereas the autocorrelation function or the ACF does not control for other lags. Now this function plays an important role in data analysis aimed at identifying the extent of the lag in an autoregressive mode. Basically, ACF PCF helps us to determine what is the best fit for doing, which model has the best fit for doing prediction. Now the two most commonly used scale-dependent measures of a time series model are based on absolute errors or squared errors. These are the mean absolute error or MAE and the root mean squared error or the RMSE. However, the most commonly used scale-independent measure is the mean absolute percentage error or the MAPE. Now the mean absolute percentage error expresses accuracy as a percentage of the error. For example, if MAPE is 5, on average the forecast is off by 5%. MAPE is one of the widely used measures of forecast accuracy due to its advantages of scale independence and interpretability. However, it has the high significant disadvantage that it produces infinite or undefined values for 0 or close to 0 actual values. Thank you.